4.2. Other questions for me? 4.2 has a lot of stuff in it. So I'm going to copy what they say. It's antiderivative as areas, but there is so much more to it than just areas. First of all, I want to talk about summation notation, also called sigma notation. What does it mean? Well, let's suppose we have this situation. I want to add 1 squared to 2 squared to 3 squared to 20 squared. There is a way of presenting this in a condensed form. And this is the name of a Greek letter. And that is the sum, S, in other words. And this is the letter. It's the same with normal S, but it's a Greek letter, and it's very, very appropriate for the notation that I'm going to show you. This is good, but it's not good enough. We're going to use it very shortly, but we're going to stretch it. Okay? We're going to stretch the sum, and it's going to look like this. You don't have to write this just yet. So right now, I'm interested in the Greek letter S, which is the same with this, which will be the same with this. But that's what we need. Why? Here's why. Because this sum has an index. The index can be normally I, J, or K. You can use any letter you want. It doesn't matter. But normally, this is what you're going to say. See, from I equals 1, ... till 20. So the index goes from 1 to the last one, which is 20. This is called the lower limit. It has nothing to do with the ILM operator. It's just the lower limit of the index. This obviously is the upper limit of the operator. From what? From I squared. So remember, this means sum. When I start with 1 for I, and I end with I being 20. So when I is 1, I get 1 squared. The sum, the sigma notation says put plus. I go on to I equals 2, 2 squared. The sum again says plus. I go on to I equals 3, ... I finish with the last value for the index, which is the upper limit, 20 squared. We don't write it like this, but we write it like this. And we know what it means. Why I need this notation, you're going to see in a moment why for this. But I have to explain what it means and the properties of this notation. So, of course, every time a notation or something is invented, properties come along with it. So if I have the sum, let's say from, I'm going to use J this time just for you to get used to it, from J equals 1 to 4, from 2J plus 1, then what does this really mean? It means when J is 1, I have 2 times 1 plus 1. The sum says plus. When J is 2, I have 2 times 2 plus 1, plus. When J is 3, I have 2 times 3 plus 1, plus. When J is finally 4, I have 2 times 4 plus 1. That's what it means. And it has 2 properties. Of course, I can calculate this if you want to. And this calculator has the summation notation. It's a super smart. The other calculators do not have the summation notation. You could, if you have this one with plus CE, then you can plug it in and you don't have I, j, k, you have to plug in x from x equals 1 to the limit of 20, and then in parentheses we have 2x plus 1, and you just click and you get the answer. Not all calculators have this, but there is a way of, there is another syntax for calculate your older versions to give that. So the answer is 440.
I thought the upper limit was 4.
Yes, it was 4 and I put 20. Okay. Yes, thank you. Got it. Yes, I should have put 4. I can do it with 4. Okay. I got hung up on 4, on 20 instead of 4. Okay. Here it is. 24. So I'm going to write it. Sum from j equals 1 to 4 to j plus 1 is 24. No, I wasn't trying to see whether you were asleep or not. I like 20 more than 4. No, I was thinking of the previous one for a moment. Thank you, thank you, thank you. Okay, so let's see what we do with this. And also, as I mentioned, I just want to show you the properties, 2 properties of sigma. Here's one. The sum of a generic term plus another generic term. It can be anything. It can be I squared plus 2i. It doesn't matter. I equals 1 through n is the sum of ai plus the sum of bi. No, I'm not distributing. I'm not distributing the sigma notation to these two. It's just that it's the same. So I either add them term by term, or I add the first one, I finish adding all of them, and then I add the second one. It's the same thing. Of course, if I have minus here, I have minus here. So these are 2 properties, but I always write them in one because they are the same pretty much. And here is another property that is extremely important, is the sum of a constant times ai from I equals 1 through n. The constant, as we know, for everything, it goes in front. So C multiplied by the sum of ai from I equals 1 through n. Okay, so what's all this about the sigma notation? Why do I need it? Okay. At this point, we want to find area or areas under graphs. Okay. So let's suppose I look at a very simple function, which is f of x equals x squared. And let's say a very simple interval between 0 and 2. Here's the graph. 1, 2, 3, 4. 1, 2. So here's the graph. At 1 is 1. At 0 is 0. At 2 is 4. Here's the graph of function x squared between 0 and 2. And I'm interested in determining this area. At this point, I cannot find the exact area. I will be happy with an approximation. So let's suppose we use 2 subintervals for now. And using 2 subintervals, I have 3 options. One option is using the leftmost point. You will see what that means in a blink. Okay, the other one, of course, using the rightmost point. Left, right, and of course the midpoint. Okay, so let's see how this works. Again, I have two subintervals that I'm going to use. I'm going to graph this again, but I'm going to take it out of there to explain what I'm doing. So this is the interval between 0 and 2. I have two subintervals, and I want to use the leftmost point. So the area with two subintervals. That will be approximately, I divide the subinterval, I divide the interval into two subintervals. And this first one doesn't have a height because I'm using the leftmost point, and it has no height. The next one has this height, and this will be the rectangle. Here I don't have anything. So how do I determine the area of this? It's the base, which is 1, times the height, which is f of 0, because I'm using the leftmost point, plus base, which is still 1, times height, which will be f of 1. Because f of 0 is 0, 1 times 0 plus 1 times f of 1, which I know is 1, so I get 1. This is the approximate area. Is this an overestimate or an underestimate? Huge underestimate. Because look at how much I'm missing. Let's look at the same using rightmost point this time. I still have 0, I still have 1, I still have 2, but this time I'm using the rightmost point. Base times height. This is the area of the first subinterval. Base times height. This is the area of the second subinterval. So the area right to will be approximately base 1 times f of 1 plus base 1 times f of 2. The answer will be 1 times 1 plus 1 times 4. So the area is 5. Is this an underestimate or an overestimate? Of course an overestimate. Why? Because now I'm adding these pieces which are not under the graph. Okay, so for now, I found a lower bound and an upper bound. The exact area will definitely be lower than 5, definitely greater than 1, for sure, no matter how many subintervals we use. Let's look at the midpoint. The midpoint will always be the best, okay? The best approximation. 0 again, 1 again, 2 again. But now I'm using this as the height. Still base, but the height is right here. Height. So this is the area with the midpoint too, which is approximately, this is 0.5 and this is 1.5. 1. Still the same. Base is still 1 for all of them. Times f of 0.5 plus base 1 times f of 1.5. So this will be 0.5 squared plus 1.5 squared. So I get 0.25 plus 2.25, right? 2.5. So 1.5 squared plus 0.5 squared. Yes, 2.5. This is the best approximation, and as expected is between 1 and 5. Question for you. After doing this little exercise, I'm going to ask you this question. I'm on 8. Do you think that if I change or I increase the number of subintervals to 4, will I get a better estimate of the area under the graph than with n equals 2. Will 4 be better?
Yes.
Yes. What about 8? Will 8 will be better?
Yes.
Yes. What about 16? What about 32? What about, where will you say, if you are using this number, then it will no longer be an approximation? With all these, it's an approximation, for sure. But where would you say enough? If you use this, for sure, you're going to get the exact area. And what, say it again.
Infinity?
What concept is this? Thank you very much. What concept is this? From this course, we used it over and over and over. What was this connected to? Which concept? From what we studied this class so far.
Is it derivatives?
Careful.
Slope.
Close. A major concept that we used all the time. It's called
Limits.
Thank you. It's the limit when n approaches infinity from the sum of all areas. And now you know this keyword. So let's see how we write all this now. Now we have everything we need.
Quick question.
Please, please, please. Yes.
Going back to the where we found the underestimate and overestimate.
Yes.
Why'd you square the second one? The last one. Sorry. How'd you get the square? Is it because of the 2? Oh, okay.
So
Sorry.
this is the same graph. I lost my other page. No, I didn't. It's right here. So we're talking about the area under the graph of x squared on the interval 0, 2. I graphed it first to explain what I'm doing and all these 3 possibilities, but then I just copied the graph directly without the x's of coordinates, the coordinate system, because it was easier for me to explain. But is it clear? I'm still talking about x squared. Here, when I square 1, I get 1. Here, when I square 2, I get 4. Here, when I square...
I got it.
Right?
I got it.
So I'm still
Yeah.
talking about this. But I'm sorry about the fact that I didn't have... I write big just for you to see what I'm writing. So, you know, this should all fit in a little piece of the paper. But I write as big as I can so everyone can see what I'm doing.
No, you're fine.
Sorry
Now I
about
got it.
Sorry about that. Okay.
No, you're okay.
Okay, so now the exact area will be limit as n approaches infinity from the sum of all areas from the first one, from the first subinterval to the nth subinterval, right? N is number of subintervals. Number of subintervals. So the limit as n approaches infinity, and we are calculating the areas. So this is the area of one of them. Why one of them? Because the sum will take care of all of them. When I is 1, I have the first one. Plus, when I is 2, I have the next one. Plus, when I is 3, I have the next one. And I finish with the last one. So now, let's see what we have here. And I have to go back to our calculations. What is this? This is the interval is a comma b. So it was 2 minus 0 divided by the number of subintervals.